Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at solubility. So this is really going to be a measure of how readily things tend to dissolve in water. So we're going to be specifically looking at ionic compounds. So these are going to be compounds made of, well, different ions bound together in a solid. So as a result, these species only are going to end up dissolving if they dissociate. So essentially, if they're strong electrolytes, they'll dissolve very well. If they're weak electrolytes, well, not quite so much. So if a species completely dissolves, so if that solid is a strong electrolyte, it's said to be soluble. Again, it dissolves in water. So let's go ahead and look a little bit more at what's happening on a molecular level. So I have a ionic solid that's made of cations and anions. So if I place it in water, what the water can do is all those partial negative charges on the oxygens can go ahead and surround a cation and say, yoinks, I'm taking you with me. And the cation says, well, I'd rather be surrounded by all these partial negative charges than have to sit in a solid relatively near other partial positive charges. So screw you guys, I'm headed home. Similarly, you'd have the partial positive charges on the waters tend to grab the anions and walk away. So as long as you don't have too many cations and anions in solution, you end up being able to dissolve quite a lot of solid. And so if the solid would rather hang out with water more than it would like to hang out as part of the solid, that's really what's going to make that strong electrolyte behavior. It's going to make it soluble. Conversely, if I have an insoluble compound, it would much rather hang out in its existing lattice than it would to essentially run away with water. And so when we're looking at trying to evaluate solubilities or insolubilities, really what we're looking at is how much do these ions like water versus hanging out with themselves. So in general, if we're looking at soluble compounds, we tend to have several key things we're looking for. So some of the most readily soluble ions are going to be small cations, lithium, sodium, and potassium. If you ever see these are always soluble. You also tend to have other molecular species like ammonia that doesn't really sit in a lattice very nicely. So it also tends to always dissolve. On the anion side, we're looking at things like nitrate and acetate. Not too surprisingly, these tend to move through aquatic systems fairly quickly as they don't sit on and bind to anything. It's one of the reasons why nitrate pollution is quite a problem. There's no good way to solidify it out because it doesn't like to hang out with anybody. It just likes to go through the water. We also have several ions that are very selectively insoluble. So things like chloride, bromide, and iodide, so all of our halides, generally will remain dissolved unless they run into silver, mercury, or lead. And as a result, this is a good way to essentially test for the presence of lead in water is to add one of these species. Similarly, if you're looking for sulfate, which can sometimes be a pollutant or a relevant ion as we've seen in lab, you can go ahead and add something like barium or lead because it's some of the only things that sulfate will bind to. On the converse side, if we're looking for things that tend to generally be insoluble, so will always form solids, hydroxides love making solids. The notable exceptions are going to be small cations, namely the ones we just ran into, lithium, sodium, potassium, and ammonia. And you'll notice that when we're talking about compounds that are generally insoluble, whether it's hydroxide, sulfide, carbonates, or phosphates, these four always lead the list. The real big difference in between these negatively charged ions is what else they might be insoluble with. So hydroxide, it's kind of soluble with calcium, strontium, or barium, but in general, if you are asked whether it's soluble or insoluble, we tend to count slightly soluble compounds as insoluble. Calcium hydroxide will break apart in water, but you need a fair bit of water to really make it noticeable. Whereas if we have something like our sulfides, they will just stay in the solid form in the presence of these. They will always dissolve in the presence of these three species, whereas carbonates, phosphates will always stay as a solid in the presence of calcium, strontium, and barium. As demonstrated by calcium phosphates and calcium carbonates are important parts of limestone in the case of carbonate, and bones in the terms of phosphates. So again, these are relatively important reactions in both the environment and in biological systems. So we have a lot of basic rules here. Trying to figure out whether a compound is soluble or insoluble can take a little bit of practice. But one of the ways we can try and walk through these lists is by going through a quick checklist. So if I want to determine whether an ionic compound is soluble or insoluble, first thing you should do is look at the cation. If it is one of our big 4 soluble cations, it's always going to be soluble no matter what. If the cation is something else, well, let's go ahead and look at the anion, because most of the other rules are based on anions. So if the anion is listed as soluble, then you're good, but make sure you're not bound to one of the exceptions. In that case, it's insoluble. Conversely, the anion is listed as insoluble, something like hydroxide, go ahead and check the exceptions, make sure it's not one of those. Otherwise, expect it to be soluble. Now, one of the big things, again, just as a quick reminder, when we're looking at our hydroxides, if it's listed as slightly soluble, generally treat it as insoluble, but realize that that might be a bit of an over-exaggeration. So, for example, if I have something like calcium or potassium hydroxide, we have potassium, it's going to be soluble. Calcium hydroxide, it's listed on that as slightly soluble, which means, in general, expect it to be insoluble, which isn't too surprising because it turns out calcium hydroxide is slightly present in a lot of lime scales. So if you see white powder on the edge of your pipes, most of it's calcium carbonates, again, a notable ion on our list, but some of it is the hydroxides. So hopefully this helps. Next time, we're going to be looking a little bit more at some specific, how these reactions take place and trying to figure out whether a reaction will produce a solid or a liquid. So we'll go ahead and put these rules to good use. Until then, take care.